Okay, today we'll talk about alternants and a certain pictorial representation of the terms in the expansion, and this is called labeled abacus. Okay, recall what was an alternant. It was, we could think of it as a certain determinant with the ijth entry of the matrix being xi raised to the gamma j. The gammas are a sequence of decreasing, strictly decreasing non-negative integers, and so when you expand this out, so think of expanding this out, say column by column, and the expression for the determinant. So what does that imply? From the first row, or let's say from the first column, you will have to pick some element, some term, then multiply that with some term from the second column but in some other row, third column some other row, and so on. Right? Last column some other row. In other words, the determinant that the expansion of the determinant looks like the following. It's a sum over all permutations sigma in Sn of the sign of that permutation times, well, something raised to the gamma 1. Right? So I've got some xi, one of the xi's raised to the power gamma 1. So this is what I pick from the first column, something raised to the gamma 2, and so on, some xi raised to the gamma n. Okay, so these are all various xi's. So this is x sigma 1, x sigma 2, and so on. So this is another way of saying what the alternant is. Okay, sigma ranges over all possible permutations of Sn. Now each such term, let's represent it by means of an abacus. So this term here, or well, along with the sign, so I'm going to think of just one of these terms for a fixed sigma, and I'm going to represent it as follows. Okay, so first let me draw what looks like the number line. Okay, so I mark some positions on it, 0, 1, 2, 3, 4, 5, 6, and so on. And what I'm going to do is to think of this as positions of beads. Okay, so this is like a runner, and I'll now start putting some beads on this. Okay, so let's do that next. So we'll place the beads in the positions gamma 1, gamma 2, gamma n. So here's an example. Let's just start with, say, gammas are the following sequence. Suppose I have 7, 5, 3, 2, 0. Okay, so there are 5 numbers in the gammas, gamma 1 through gamma 5. These are the numbers. Now what this means is that I think of this as an abacus in which I have placed beads at positions 7, 5, 3, 2, and 0. But now these beads are also labeled. Okay, that's why we call this a labeled abacus. So I think of these beads as having labels, and the labels will be, I can think of them again as 1, 2, 3, 4, 5, but to establish the connection directly with the determinant, let's label them x1, x2, x3, x4, x5. Okay, so I have 5 beads. Beads are now labeled x1 through x5, bead labels. x1, x2 till x5, and I can place them in any order. Okay, so all possible permutations of these 5 beads, right? But the positions of the beads are fixed. They can only be in the numbers 7, 5, 3, 2, and 0. Okay, so there will be 5 factorial different ways, all possible permutations of arranging these beads, and each one corresponds to one term in this summation. So what does this term here correspond to? X sigma 1 power gamma 1. So these are, remember, this is gamma 1, right? 7 is gamma 1. This is gamma 2, and so on. Gamma 3, gamma 4, gamma 5. So what I'll do is, to represent the term that's written here, x sigma 1 power gamma 1, I will think of this bead as being labeled x sigma 1. Okay, so this is some xi. This is another xi, x sigma 2, x sigma 3, x sigma 4 and x sigma 5. Okay, so the beads are labeled by these x's, and such a configuration of these 5 beads placed at these positions and with these labels I will call a labeled abacus. Okay, now this is really the same piece of information as a single term in the expansion of the determinant. So let's make that more precise. So given a labeled abacus, we will define something called the weight and the sign. Okay, so definition, the weight, it's denoted WT of A. Okay, let A be a labeled abacus. The weight of A is just defined to be the following. It's just remember you would have put some xi, what we call x sigma I, in the gamma ith place, right? So you look at what bead you placed in which position and you take the product of all that. So the gamma keeps track of the power. Okay, so that's just the weight of that labeled abacus. The sign of the labeled abacus, the sign of A, is just the sign of the permutation, that you get when you read these bead labels from right to left. So this is just the sign of the permutation obtained by reading the bead labels from right to left. Bead labels from right to left. Okay, so let's just do a very simple example. So this is slightly larger, the one that I drew. So let's take something somewhat simpler. So let's take gamma to be 1, 2 and 4. So I have to place beads in positions 1, 2 and 4. Okay, and suppose I place the following beads, say in position 4 I place the bead x2, position 2 I place the bead x1 and x3 in position 3. Okay, so what are my various parameters? Gamma here is the tuple 4 to 1, my number n is 3. Okay, and this is a certain configuration of beads, x2 in place 4, x1 in place 2 and x3 in place 1. So what's the weight of this abacus? So let's call this labeled abacus as A. The weight of this abacus will just be, so I look at, I can do it any which way. So I look at x3, it's in position 1. I look at x1, that bead is in position 2. x2 is in position 4. Okay, so I take each xi and I raise it to the power of the position in which it lies. So another way of writing the same thing is to say xi power the position of the ith bead. Okay, I goes from 1 to 2. So that's that term. And what's the sign in this case? The sign of A is just, well, it's the following. I read the bead labels from right to left. So what are the bead labels here? x2, x1, x3. Okay, so I've just read the labels, and so I think of this as the permutation 2, 1, 3. Okay, and the sign of A is by definition the sign of, so this is just intermediate step. This is just the sign of this permutation 2, 1, 3. Now 2 and 3 is just a transposition which interchanges 1 and 2, right? So the sign of this permutation is a -1. Okay, and similarly, so you can imagine how this works in general. In this particular example, there are 6 different ways of placing these 3 labeled beads on these 3 positions on the abacus, and each such configuration will give you a certain weight and a sign. Okay, and now here comes the simple fact. which is just maybe a simple rephrasing of the expansion of the determinant. It says that the alternate A gamma, or the expansion of the determinant, is simply the following. You can think of it as the following sum, sine of A times weight of A, as A varies over all labeled abaci with bead positions given by gamma. That is gamma 1, gamma 2, gamma n are the positions. Okay, good. Now let's look at a special case, which is the Vandermonde determinant itself. So here's the Vandermonde example. So recall that's what we call delta, the bead positions. So in this case, I'm going to look at the alternant corresponding to delta. So it's n minus 1, n minus 2, 1, 0, and recall A delta is exactly what we call the Vandermonde determinant. Right? This is the famous Vandermonde determinant. And if you want to think of this in terms of the abaci and so on, what this means is I have to look at all possible abaci in which the bead positions are 0, 1, 2, 3 till n minus 1. So the beads sort of live on the first n positions on the abacus. Okay, so somehow the most compact abacus you can imagine. It's all the beads are clustered together there. There's no gaps between beads. Okay, and recall also that we actually know an expression for the Vandermonde determinant. So A delta of x. So you've probably done this this nice exercise. Show that the Vandermonde determinant can actually be written as a product, and it's just the product of xi minus xj over all I less than j running from 1 to n. Okay, and you probably also remember how the proof went. You just look at the determinantal expression for the Vandermonde and then observe that if you put xi equals xj, then some two columns become equal. Okay, and which tells you that xi minus xj must be a factor of the polynomial, the determinant itself. Now let's just recall that argument quickly in slightly more generality. So let's actually consider a general gamma, not just delta itself. So let gamma just be an arbitrary decreasing sequence, and let's remember what A delta was. It was that determinant, again x1 power gamma 1 blah blah blah, x1 power gamma n, x2 gamma 1, x2 gamma 2, etc. And again observe that if you put, so all the way till xn power gamma n, and recall now that if you put xi equals xj in this, so xi equals xj, putting this, what you conclude is that A gamma of x has two equal rows and therefore the determinant must be 0. Okay. Now what does this mean? This says that, so what is A gamma x really? A gamma of x was a polynomial in the variables x1, x2, xn. In fact, we said it's an alternating polynomial. It changes sign if you interchange any two variables in general. Now A gamma of x belongs to this, and it's 0 whenever you put xi equals xj. So what this means is that, I mean, one way of saying it, you can think of this as polynomials in just the single variable xi. Okay, so do the following: remove xi from the list, think of this as the space of coefficients, and then think of it as a polynomial in the one variable xi. Okay, and now xj is a constant really. You're thinking of the remaining guys as constants. So when you plug in xi equals xj, this polynomial vanishes. So what this means is that A gamma of x is divisible by xi minus xj. Okay, is divisible by xi minus xj, and this is now true for all I not equal to j. Okay, and just for, let's not repeat terms, so let's fix I less than j in this case. So each of these guys divides it. Okay, And these are all, in the full ring Z of x1, x2, xn, the terms xi minus xj, the polynomials, are all obviously reducible polynomials. They're all just degree 1 polynomials. And this is a UFD, a unique factorization domain, and so on. So what this implies is that if you actually, it's divisible by each of them, and therefore it's divisible by their product. Divides A gamma of x. Okay, because they are all distinct irreducible elements in this unique factorization domain. So this, on the other hand, is A delta of x. So what we have just concluded, sort of by repeating the same argument which one uses to show that A delta of x is actually the product xi minus xj. So I mean, you can actually use the same argument to show that A delta is the product, just by comparing now degrees on both sides and so on. So I won't get into that right now, but what we have just shown is that A delta always divides A gamma. Okay, so any alternate is always divisible by this special alternate A delta. Okay, and this quotient is sort of our object of great interest. So let's define this. So now I'm going to say let lambda be an n tuple, lambda 1 greater than or equal to lambda 2, and so on, lambda n greater than or equal to 0, so that lambda plus delta is a strictly decreasing sequence, as we saw before. The sure polynomial, so this is the definition, the sure polynomial S lambda of x, S sub lambda of x, x1, x2, xn, is defined to be the quotient. Take the alternate A lambda plus delta of x. Okay, as we just observed, this alternate is always divisible by the alternate A delta, okay, or the Vandermonde determinant. So you divide that alternate by the Vandermonde determinant. Okay, and what you get is what we'll call the polynomial S lambda of x1, x2, xn. Now, two quick facts about this polynomial. Number one, observe that both lambda plus delta as well as A delta are alternating polynomials. What that meant was, if I interchange any two variables xi and xj, they give you a minus sign in front. Okay, but suppose I interchange xi and xj now, the numerator will give me a minus sign, the denominator will give me a minus sign, and they will cancel. Okay, so what this means is that S lambda itself, the quotient, will be unchanged if you swap xi and xj. In other words, this is now a symmetric polynomial. Okay, it's a quotient of two alternating polynomials, so this is actually a symmetric polynomial. And fact 2, it's actually a homogeneous polynomial as well. Okay, and that's because each of the alternants is a homogeneous polynomial in the x's. So I'll just call it x now. S lambda of x is in fact a homogeneous polynomial. And what's the degree of degree? So the degree of the quotient is now just going to be the degree of the numerator minus the degree of the denominator. And if you sort of remember what the degree of the quotient was, lambda plus delta, right? So this degree of lambda plus the degree of delta.